Howdy y'all, welcome to Ductwork Engineering. Alright, so I'm going to go over a shell balance problem from chapter 2 of this book, which is also referred to as the Bible of Transport Phenomena by my professor. I chose this particular problem because it was on the midterm I just failed. Now, chapter 2 goes over shell momentum balances and velocity distributions in laminar flow. There are a couple different ways to tackle this kind of problem, but I'm going to go over it in a way that shows you as much of the derivations as possible and basically where everything comes from. So hopefully by the end of this video you can tackle any similar shell balance problem on your own. The solutions I found online just takes an equation from the book and it skips a lot of the steps, so that's kind of confusing, but I'll still post it in the description in case y'all want to use it and find it more useful. Alright, so today we're going to deal with an annular flow with inner cylinder moving axially. You may choose to pause the video now and read it before I get started. Okay. In these types of problems, there are a few important steps. First, we need to state all the assumptions and determine the boundary conditions. Next, we need to use Newton's laws of viscosity under the appropriate coordinates. Then we solve a momentum balance. From there, we can finally start the actual problem for what it asks for. Alright, so to start off, we should make a poor sketch of the gizmo so that we can get a better understanding what's going on. The coordinate system can be set up so that the z-axis goes here and r goes here. And obviously z is for axial motion where r is radial because r is the radius. Okay, we got a pipe and a rod inside. Because this is a chapter 2 problem, it's safe to assume that we're working in steady state and with laminar flow. To simplify things, we're going to neglect edge disturbances. The problem is set up so that the axial velocity, or v sub z, is only a function of r, the radius. That makes sense because we see from our drawing here that the water is flowing axially only, but the magnitude of the velocity depends on the distance from the center of the pipe. See, the lines are smaller and longer here. So in other words, it just depends on the radius. Furthermore, we have no radial or tangential velocity. Also from the problem, we see that the pressure in the inlet and outlet is constant, so P for pressure is constant. We can now set up some boundary conditions like velocity v sub z at r equals 0 because of the no-slip assumption. Next, we can state that at radius kr, the velocity is v sub naught. And we basically just get that from going back to our problem and seeing this here and over here. Okay, so now we can start with our next big step, which is Newton's law of viscosity. We're doing cylindrical coordinates because we're working with a pipe. So what you're going to want to do is go to Appendix B and pull up Table B1. So let's get that book here. Okay, if we scroll down, we see the first one shows Cartesian coordinates, but we don't need that. We need cylindrical coordinates, so that's over here. This shows all the shear stress equations that we're going to need to pull out and put onto our little workspace here. So I'm going to go ahead and copy that. Okay, now that we have everything written out, it might look scary at first, but if we just go by it slowly, we'll see that everything kind of cancels out nicely and it looks much better, so don't worry. Alright, let's just start with the first one, okay? So we have a whole lot going on, okay, but we see here that the change of radial velocity in respect to r is actually going to turn into 0 because, well, we don't even have radial velocity, and also it's not even going to be changing in respect to r. So that goes to 0. And then we have this del dot v. So from the book we saw that del dot v is equal to this. We know that v sub r is equal to 0 because there's no radial velocity. And then also the change of tangential velocity is 0. And then now there is axial velocity, but it's not a function of z. It doesn't change based on the axial direction. Remember, we said it only changes on the radial. So that equals 0 because v sub z is a function of r only. So this means now that the entire thing del dot v equals 0, and that really simplifies a lot. So that all goes to 0, and now we go to the next one. Like I said earlier, this goes to 0, There's no radial velocity, that goes to 0. This whole thing goes to 0. And now the next one, like I said, there is axial velocity, but it doesn't depend on the z. It depends on the radius, so that goes to 0. This goes to 0. Moving on, this it goes to 0. There's no tangential. This goes to 0. Again, we have this goes to 0, and this goes to 0. So far, this whole thing is 0, 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 and this whole thing is 0. And now with the last one, we have the change of velocity, or the radial velocity in respect to z. That's 0 because there's no radial velocity, right? But now the next one, we have the change of the axial velocity in terms of the radius. Remember what we said earlier, that it actually does, it's only a function of r. So this actually does not become 0. So this whole thing results in becoming just mu multiplied by v z r. And these could actually just become the regular z r. See, so this whole scary table of equations just becomes only this that we have to worry about. Okay, now we can finally list various contributions to the z momentum balance. Now this part is kind of hard to comprehend, so I'm going to draw yet another sketch to clarify things. Here we have the cylinder from earlier, but I've added this shell diagram, which is like kind of shaded in green. So basically for this step, what we need to do is calculate all the momentum flux, or just account for all the momentum flux coming in from every direction. We're going to start from this side here, the momentum flux coming in from this side. So basically what the momentum flux is, it's denoted by this phi with two subscripts. So the first subscript z here, it just means the direction that the momentum is moving. So we see here it's just this axial direction, z. But the second subscript, that denotes where the fluid is flowing. So in this problem, it's always going to be moving in the z direction because the fluid just has axial velocity. And since we're starting on this side, z is equal to 0. Now the whole momentum is phi multiplied by the cross-sectional area. The cross-sectional area in this case will be the shaded part of the shell. So like this, so this is like the area of a disk, which will basically turn out to be 2 pi r delta r. That's the area. And then we still have the phi z at z equals 0. So now we can move on to the other side, which is here. So the same things apply, it's just the area, and it's still the same area, so it's 2 pi r delta r, and still the same subscripts, because it's just that it's still in the momentum in the z, with the fluid moving in z, but this time it's when z equals L, because it's all the way at the end. Now we're going to go and look at it approaching from like the R axis. Now, so the first one here we have is coming from like the center of the whole like cylinder and moving outward. So basically from here, you're going to want to start from the center of the cylinder and calculate the momentum flux. So we're going to start with the area again. In this case, the area is going to be like the surface area of the cylinder. So we have 2 pi L R, and that's going to then be multiplied by phi, but this time the momentum is moving in the R direction, so it's first subscript R, but the fluid's still moving in the Z direction, so RZ, and then it's at R. Now, moving on from there, we have it basically like how we did before on the other side. This is the same area, 2 pi LR, but this time, and then also the RZ, but this time it's R plus delta R because we've moved up by delta R. It's also important to note that sometimes the problem will be affected by a gravity force. So then for gravity, you have volume times density and the gravity acting on Z. But since we are working in a horizontal pipe, this doesn't even matter because it's just going to be 0. Gravity is not that important in this case. But in other problems, it might be important. So now that we have everything accounted for, we can calculate the entire thing. We have the momentum in minus the momentum out plus gravity force equals 0. So let's write down all the momentums we have gathered up. Okay, so now that we have everything written out, let's actually solve this so we can get our velocity distribution. Okay, now I'm going to separate the like terms. So here we are. And now the next step would be to divide both sides by 2 pi L delta R. So let's do that. Divide by 2 pi L delta R. So if we do that, this term will go away, this term will go away, this will go away, this, and then this will be all over delta R, and then this whole thing is just going to be over L. So let's see. Okay, now the next step, we can take this term here and apply a limit as delta R approaches 0. Alright, now this is actually the definition of a derivative, if you guys remember from like pre-calc. So this will become d dr of r phi rz. So now I just moved it to the left hand side and we still have our right hand side right here. Now we're going to work on our right hand side. So this phi z, these phi z terms, we can define that. So the momentum flux is equal to pressure plus the shear stress plus density times the velocity. So we can apply them to both of the phi terms. And as you can see here, we've determined that the pressure from the inlet Z equals 0 and the pressure at Z equals L, so this P0 and PL, they're equal, they're the same. So this is plus, this is minus, but since they're the same thing, they cancel out. So these terms cancel out. And now the velocity terms, the axial velocity is going to be the same at the beginning and at the end in terms of just the z. These will cancel out as well. So this whole thing just becomes 0. If we plug that back into our equation that we had earlier, it's just that ddr r phi rz is 0. Okay, now we can apply Newton's law of viscosity. So we could take the phi rz term and define that real quick. That's just the shear stress plus the density times velocity. Okay, earlier we defined what the tau rz was equal to, which is tau rz is equal to negative mu dvz dr, and that's just from when we did the Newton's law of viscosity part. Okay, also we know that the radial velocity is 0, so this part becomes 0. So all we're left with is just the shear stress, and we can plug that back into the equation. Now, I moved the negative outside, but we can also move the viscosity outside as well because it is constant, and that was based on our assumptions. So now we have this, we can now multiply both sides by a negative viscosity, so this will just go away. And so we're going to be left with this. Now we integrate it, and we're just left with this inside term, which is going to be r dvz over dr, and don't forget the constant, so c1, because we integrated. Now we could multiply both sides by dr, so dr goes here, and then we move the r term to the right as well, so r, and then we can integrate both sides again, so that will give us vz equals ln of r, or like multiplied by c1 plus c2, and I'll rewrite that here. Okay, so now we have two unknown constants. We're going to have to apply our boundary conditions. Earlier we defined our boundary conditions depending on how far we are from the radius of the cylinder. So for the first boundary condition, which is at radius r, we know that the velocity, or the axial velocity, is 0. Now the second boundary condition, we know that at a radius of kr, the velocity is v naught. And just to show you real quick, that's from our drawing here. It is 0, and then here it is v naught. Okay, back to our problem. So this will be equation 1, and this will be equation 2. If we subtract equation 2 from equation 1, we can find what the first constant is. So we can simplify this. We know that the C2's go away because it's a plus and minus. And then we could combine like terms. So it's just C1 multiplied by ln kr minus ln r. And remember that ln of like a minus ln of b is equal to ln of a over b. So we apply that and we can simplify the equation and get that c1 equals v naught over ln of k. Now we could plug this back into equation 1 and we can find what c2 is. So moving everything so that c2 could be by itself, we get c2 equals negative v naught ln of r over ln of k. Now we have both of our constants, so we could plug it back into the original equation, which is right here. Plugging it back into the original equation, we get that VZR equals V naught over ln of k times ln of r minus V naught ln of r over ln of k. Now this is basically our answer, but we could simplify it a bit more to make it look nicer. And there you go. This is our velocity distribution. Alright, so we're like 18 minutes in and we only found part A. That's just... Alright.